Muy buenas tardes. Es un gusto agradecerles el interés en este ciclo de conferencias de Universidades por la Ciencia, organizado por Fundación UNAM, por el Colegio Nacional, por la UNAM, la Universidad de las Américas y un conjunto de universidades en el país y en el extranjero. El consorcio inicialmente formado para dar conferencias sobre diferentes temas, se ha ido ampliando sus actividades y nos da muchísimo gusto el que nos acompañen y que tengamos, que podamos llegar a muchos otros lugares aquí en México y pues fuera. Participa el día de hoy y es un placer el agradecerle que haya aceptado la invitación la doctora Eisel Sartbaeva. Ella es investigadora en la Universidad de Bath en Inglaterra, en el Reino Unido, y la doctora Eisel tiene una trayectoria realmente muy interesante y su trabajo de investigación tiene, además de todo el reto científico, tiene enormes implicaciones para la salud. La plática es sobre las vacunas y es un nuevo método de nanotecnología para poder almacenarlas y transportarlas de una manera segura. Las vacunas, la mayor parte, y ella nos lo va a comentar en la conferencia, se pierden por los problemas ambientales en el transporte. Las vacunas son particularmente sensibles a los cambios de temperatura, tienen un rango extremadamente pequeño de unos cuantos grados y arriba abajo de ese rango las vacunas, las proteínas de las vacunas se dañan. Entonces esto ha sido un reto, el poderlas llevar y transportar de una manera segura y que las vacunas que se pongan, sobre todo los niños, sean activas, sirvan. Realmente ese es el principal problema que se tiene. Y la doctora Isel tomó de una idea a convertirla en realidad, lo que demuestra pues cuando se tiene una pasión por la investigación. Entonces realmente es un gusto el tener a Eisel Sartbaeva hoy con nosotros. El ciclo de conferencias organizado por Fundación UNAM es parte de las actividades de la Fundación y en estos meses estas actividades se han ampliado de una manera muy amplia. Tenemos además del ciclo de conferencias, el ciclo de documentales de divulgación científica y Fundación UNAM tiene el Foro 2020 que ya tiene varios años de tener un éxito extremadamente alto. Entonces, voy a pasar la palabra a nuestro presidente de Fundación UNAM, el licenciado Dionisio Meade. Nos acompaña también el grupo de Fundación UNAM, la directora ejecutiva, la licenciada Araceli Rodríguez, y realmente Fundación es una de las riquezas que tenemos en la UNAM. El número de afiliados es extremadamente alto y los programas, sobre todo los programas de becas, son los que permiten a una buena parte de nuestros estudiantes el poder concluir sus estudios de una manera exitosa. Realmente el tener a Fundación UNAM con nosotros es siempre pues, un motivo de orgullo. Entonces, le cedo la palabra con mucho gusto al licenciado Dionisio Meade.
Muchas gracias, Jaime. Nuevamente subrayar que para Fundación UNAM es una gran oportunidad y nuestra gratitud al Colegio Nacional, nuestra gratitud a la Universidad de las Américas Puebla y nuestra gratitud también a las universidades que forman este consorcio que se ha vuelto cada vez más numeroso, que se ha vuelto cada vez más profundo y que está ilustrando casi de manera piloto de las capacidades que pueden derivar de una vinculación de esta naturaleza. Esta formidable idea de crear el consorcio vino a definirse una vez que se hicieron públicas las dificultades para los contactos presenciales. Entonces se pensó que una manera de superar esta adversidad era vincularnos en redes, era vincularnos en línea. Y la verdad es que las capacidades que se han generado a través de esta modalidad de enseñanza, de esta educación a distancia Y de esta capacidad de intercambiar conocimientos, de intercambiar experiencias, de sumarnos a espacios de investigación, está resultando muy, muy importante. Hoy, por ejemplo, tenemos la presencia de la doctora Eisel desde la Universidad de Bath y tenemos una presencia transoceánica para poderle escuchar. Y eso multiplica también los beneficios de quienes pueden escuchar estas audiciones. Ya habíamos mencionado que casi por capacidad física, quienes más podían escuchar algunos de nuestros eventos presenciales, pues podían ser 100, 150 gentes. Hoy, en cambio, a través de esta transmisión en redes, se cuentan por cientos de miles. Y eso acredita las capacidades y las potencialidades que derivan de una experiencia de esta naturaleza. Subrayo la importancia del tema que hoy nos toca. Yo creo que ciertamente las vacunas han sido siempre un tema de gran interés para la humanidad, pero hoy quizá lo son más que nunca. Todo el mundo revisa la información cotidiana para saber qué tan cerca está la elaboración de esta vacuna con la que podamos hacer frente a esta epidemia, a esta pandemia brutal que ha venido a cambiar el rostro del mundo. Y ciertamente ya se anticipan que una de las dificultades a que habrá de enfrentarse la aplicación de estas vacunas es, primero, su elaboración, el llenado de los recipientes, la distribución equitativa, y ciertamente si alguna requiere un espacio de protección en condiciones térmicas, la distribución sin que se pierda esta capacidad, esta eficacia que las vacunas deben traer consigo. El problema de la distribución de las vacunas es un enorme problema logístico, lo sería inclusive si no tuviera que sumar a sus complejidades el de cuidar un espacio térmico que le permita que no se eche a perder su eficacia. Ojalá que las nuevas vacunas no requieran esta exigencia, pero ojalá que si lo hicieran, las investigaciones de la doctora Eisel permitan que se puedan transportar con seguridad, con protección, como dice Araxi, en un espacio de termoestabilidad para que su eficacia no se pierda en la distribución. Es una pena lo que se nos dice a la entrada, que muchas de las vacunas pierdan su eficacia cuando son tantas las necesidades, tantas las vidas que se podían salvar si llegaran a su destino adecuadamente. Hoy, quizá, como parte del desafío en la definición de esta vacuna, habrá que sumar desde su origen esta investigación de la doctora Eisel para que la protección de las vacunas pueda permitir que su eficacia no se menoscabe en la distribución. Nos sentimos muy contentos de participar en este evento. Agradecemos nuevamente a Jaime Urrutia esta posibilidad de participar juntos en este evento, a la Universidad de las Américas, y vemos claramente cómo se cumplen los objetivos de la Fundación: la docencia, la investigación científica, la difusión cultural. Cada una de estas presentaciones se identifica perfectamente con cada uno de estos objetivos. Por eso para nosotros es un privilegio sumarnos a este esfuerzo y ver que nuestra universidad, la Universidad Nacional Autónoma de México, la más importante sin duda de América Latina, participa también activamente en este proyecto. Gracias de nuevo, bienvenidos todos y listos para escuchar con el mayor interés esta presentación la tarde de hoy, noche allá en Inglaterra. Muchas gracias.
Thank you very much. Muchas gracias, licenciado Dionisio. Muchas gracias, doctor Urrutia. I'm going to switch to English to introduce Dr. Aisel Sarteva. She is an academic at the University of Bath. Before I tell you a little bit about her amazing career path, I just want to say thank you to anyone from the University of Campinas in Brazil who have just joined the Universities for Science Consortium, and also a big hello to anyone who's watching from Bath. So Aisel did a physical science degree at the Kyrgyz Russian University in Kyrgyzstan, Back then, she was the only woman, and she was a minority, both in terms of her origin and also in terms of being one of the few women in the course at the university. After a stint volunteering for the British Council in neighboring Kazakhstan, she got a scholarship to do her PhD at no less than the Cambridge University, and then moved to Arizona to do a postdoc at Arizona State University. And from there, moved back to the UK and did a postdoctoral stint as a Gladstone Research Fellow at Oxford University. And it was then that she started to develop her ideas on how to preserve vaccines. And she, in 2010, obtained a Royal Society Fellowship, which is a very prestigious fellowship that allowed her to establish her career as an independent scientist and have her own research group. Over the last 10 years, it's been a pleasure to have known Hazel and to have witnessed what was originally just a dream to blossom into a fully funded project with lots of collaborations and most recently actual success and proof that preserving vaccines using nanotechnology is possible. So I think, well, there's nothing more to say that welcome, Hazel. Thank you very much for accepting this invitation, and I really, really look forward to listening. How is it that you've gone from a very good idea to a very good result?
Thank you very much, Araxi, for inviting me and for introducing me. And thank you very much for the introduction before. It's lovely to be here with you. And I'm going to start sharing my screen in a second. Tell me when it's working, and then I will start my talk. Is that showing all right? Okay. Brilliant. So thank you very much. And I will start talking. Please think of questions and I will be happy to answer at the end of the talk. So in my talk today, I will talk about vaccines and I will talk about a new solution for cold chain problems for vaccines. Just to give you an overview of my talk, I will start by talking about vaccines and vaccine cold chain. I will then talk about silica, because silica is what we use in our method. And the method we've developed is called ensilication. And then I will show you some of the latest data and results we've obtained recently. And I will talk to you a little bit about our future plans. So to start with, I always like to start with slides about vaccines, because first of all, we all know that vaccines work really well. Vaccine is one of the best, one of the greatest interventions in healthcare, because it has been saving lives, it is saving lives, and in the future it will be saving lives. This is a really good infographic which shows that vaccines work. This is infographic specifically for US. You can see here that pre-vaccinations, so this is for 1900, we had a lot of cases of a lot of vaccine preventable diseases like measles, pertussis, mumps, rubella, and others. And after vaccination has been introduced, so here on the right-hand side, we are looking at the cases at 2010, we can see that the numbers have precipitously dropped down, which really shows us, even though the population has risen dramatically between those two time frames, we see that the number of cases has really fallen down dramatically. So this infographic is just for US. If we look for the whole world globally, the number of children children deaths from vaccine-preventable diseases have also dropped enormously. So here we can see statistics between 1990 and 2017. And the numbers which we are looking at here is that we had something on the order of 12 million children deaths in 1900s. Almost half of them were from vaccine-preventable diseases. And for 2017, we can see that this number has dropped to about 6 million. Unfortunately, about 2 million are still deaths from vaccine-preventable diseases. So these are deaths amongst children until up to 5, mainly infants who are dying still because they are not being vaccinated. So in majority cases, we physically cannot bring vaccines to those children. So we don't have time to vaccinate them. And this is the big problem. So DTP vaccine, diphtheria, tetanus, pertussis vaccine, is a model vaccine which WHO uses in order to look at all vaccination programs around the world. So if we look at the DTP coverage, you can see this is a snapshot for 2016. We can see that in some of the countries, we have very low coverage. So for example, the 3 countries which are in red here are Ukraine, South Sudan, and Somalia. These are the countries where there was a conflict in 2016, and hence the number of vaccinations have dropped precipitously. But we can see also in some other countries where there wasn't a conflict at the time, countries like India, Indonesia, where the population is rising very rapidly, there are still some problems with vaccinations. And again, a lot of it is because we physically cannot bring those vaccines to people. So on average, in low-income countries, we have 16% fewer infants being vaccinated with the DTP vaccine compared to the developed countries. Looking specifically at Latin America and the Caribbean countries, we can see that we have quite good statistics. So this is for 2018 from UNICEF. However, we still have some problems in the countries which are outlined in yellow and dark blue here. You can see these are the countries where we have vaccination below 60%. In order for us to have herd immunity, in order for a majority of the people to be protected with vaccines, we want to have vaccine coverage more than 90%, or ideally 95%. So having vaccination rates below 60% rings alarm bells usually, and this is really problematic areas which need to be solved somehow. So there needs to be like a holistic approach to really being able to see what exactly is happening in the specific countries and how this can be addressed. So let us talk about the vaccine storage specifically. So we know that vaccines work. They're really good at preventing diseases. Why do they break? Well, vaccines have to be stored in a very narrow temperature range. So the good temperature range for them to be stored is between 2 and 8 degrees centigrade. Anything above or below leads to the vaccine denaturation. So as soon as the temperature goes above 8 degrees, vaccines denature because the proteins inside them unfold due to the increase in temperature. So we have this entropic effect. When we drop below 2 degrees, vaccines they denature because in a lot of them, alum adjuvant, which is present, would freeze and break the active ingredients. So they break differently at cold or hot temperatures. And on the right-hand side here, you can see that we have sort of divided majority of our vaccines. I'm talking about children vaccines. We've divided them sort of into two types. We have one types which are in green and yellow here. They are really freeze sensitive. So these are vaccines like DTP, Hpv, Hpv. All of those vaccines cannot be lyophilized. They cannot be freeze dried. So they're really freeze sensitive. So as soon as the temperatures drop down, these vaccines would start breaking. And then we have other vaccines which are in blue here. So these would be the vaccines like yellow fever, BCG. BCG is against tuberculosis, MMR, measles, mumps, rubella, and some other vaccines which are really heat sensitive. So these vaccines, they wouldn't mind to be frozen, but as soon as the temperatures go above 8 degrees, these are vaccines which would start breaking down. So both of these obviously are not good temperature ranges, so they both need to be addressed. When I originally started thinking about this, I was thinking about keeping vaccines at room temperature, so I was mainly thinking about heat denaturation, but we are also now looking at cold denaturation too with our method. So we have this big problem. The problem is called cold chain. So cold chain has been devised for vaccination programs about 50 years ago. So about 50 years ago, WHO decided we need to vaccinate people, and obviously cold chain has been developed for transport and for storage. So what it means is that as soon as vaccines are produced, they have to be refrigerated and they have to be kept between that 2 and 8 degrees. And if they're being transported around, if they're being airlifted, they have to be refrigerated all the time. So obviously, if they are airlifted, then when they arrive to the country of destination, they have to be stored somehow and then distributed around. And again, all of this has to be cold refrigerated. And eventually, they're then transported to the local areas where the people are going to be vaccinated. And up until the point of the vaccination, these vaccines have to be refrigerated at all times. So you can see already that it's quite a complex system, quite a complex logistic system, where at every step, you need to have a cold chain to be present. And obviously, if something goes wrong, for example, if there is no electricity, or if we have breakages in the equipment, we have breaks in the cold chain, and that means that that would lead to the vaccine wastage. So what we see today is that up to about airlifting stage, we lose on average about 5% of the vaccines due to breaks in the cold chain. But it's really the last leg of the journey from the local hospital to the patient, or from the big hospital to the local rural hospital in some areas. The last leg is where we are losing majority of the vaccines. So up to 90s, we used to lose anything up to 80%. And I think today, majority of the providers are admitting that today we are losing about 50% of the vaccines. Now, when I first started looking at this problem, I was utterly shocked with this number. I just couldn't believe that we are losing so many vaccines. And I couldn't comprehend why we're losing so many vaccines until I saw these pictures. You can see here that it's really the last leg of the journey where we have the big breakages. Because in the last leg of the journey, a lot of the vaccines in rural areas, especially in low-income countries, are being transported not in refrigerators, but in cool boxes. And you can see here they're being transported on a camelback, on a horseback, or on a bicycle. And these vaccines in cool boxes, they start degrading pretty much as soon as they're being put in those cool boxes. So that really explains why we lose so many vaccines in the last leg of their journey. So, okay, I've told you that we have a big problem with the cold chain. And obviously, we want to do something with this outdated system. It's now been 50 years since it's been devised, and it worked really well. It works quite well in developing countries. It worked pretty well in some low-income countries, but it is clearly not working everywhere, and it is clearly problematic. Now, let us look at some successes. Now, vaccination has been incredibly successful. We have managed to completely eliminate smallpox in humans. So it was a lethal disease which prevailed up until 1970s. And with a global vaccination push, it's been completely eliminated today. Another disease which was prevalent in cattle in 1980s called rinderpest also has been eliminated. So I think it was called something like a cattle plague. And again, with the big push for vaccination, it's been completely eliminated. The third disease, polio, is almost eliminated. So we only have today 3 countries around the world where we still see polio, but WHO and UN have a goal to eliminate polio by 2025. So I'm hoping that by then we will be able to say that polio has been completely eradicated. Another interesting fact which I found was that actually a Latin American region was the first to declare completely polio-free, and the last case of polio was in Peru in 1990s. But since then, polio has not been in Latin American countries. What's interesting about all of these 3 diseases is that they have vaccine formulations which are stable at room temperature. So this is really telling us that if we want to be successful at eliminating diseases, we want to make our vaccines stable at room temperatures, because this really helps us to be able to push on vaccinating as many people and to have this herd immunity developed in all of the population. Now, I'm not going to be talking about complex modern vaccines which are RNA or DNA based. I will mainly be talking about sort of older vaccines and vaccines, children vaccines mainly also, which are made, which have in their structure proteins. So these usually are vaccines which are made out of viruses, viral vectors, viral particles, or protein complexes or peptides in them. You can see that in all of those examples here, the structure of each of them will consist of proteins. So for example, on the left-hand side where we have a virus, we can see that in each color indicates a specific protein, and then those proteins come together in the shape of a virus. So all of those systems have proteins as their building blocks. And we know that protein structure can be divided into 4 hierarchies. So we have primary protein structure, which is the amino acid chain, which is a sequence of the amino acids connected to each other. We have secondary protein structure where they fold into some kind of alpha helices, beta sheets, loops. And then we have tertiary protein structure where the whole protein folds together. And then obviously quaternary protein structure where we have several or many proteins coming together and building that virus, for example, or a viral particle. So I will be talking about protein denaturation. And when I talk about protein denaturation, I will mainly talk about denaturation of the quaternary, tertiary, and secondary structure. So what we find is that majority of the time upon heating, it's not the primary structure of the protein which breaks down. It's not a chemical reaction, but more it's an unfolding of the amino acid chain. So it's the loss of quaternary, tertiary, or secondary structure, which happens due to the heating, for example. So we can see here, there is a video of a simulation of the protein being heated, and as it's being heated, it's unfolding. And as it's unfolding, it's losing its quaternary, secondary, and tertiary structure. You can see that it's losing its alpha helices, beta sheets, and by the end of the simulation, it's completely unfolded. So the analogy here, a very good analogy here, is to imagine an egg. When we start with the raw egg, it has one structure. But when we boil that egg, what happens is that all of the proteins inside that egg, they unfold. They all tangle up, and we all know that it's impossible to unboil egg back. In the same way, once the proteins have unfolded and lost their quaternary, tertiary, and secondary structure, we cannot bring them back, which means that, like in marine diatoms, we can actually grow that shell to fit the body, to fit the protein. So this is the protocol which we have devised after many years of experimentation. And you can see here in the left-hand side, we start with the protein in buffer, we add silica to it, and something starts happening to this protein. So there are actually 3 physical chemistry processes which are happening here. So the first two processes are sol gel. We're using sol gel chemistry here. So we have gelation. So we have the silica sort of coming in contact with the protein and not really attaching, but sort of becoming very close to the protein. And then the silica starts growing all around it. So this is the condensation process. And then we have the third process, which is precipitation, which is when the whole protein gets surrounded by the silica, we create a nanoparticle. And this nanoparticle can then grow bigger. And when it grows to something around 100 nanometers or more than that, then it starts crushing out of the solution. So it precipitates out in the powder form. So when we see this precipitation happening, we know that we have nanoparticles in our solution. We then can collect them and we gently dry them. And after this, we wether this powder. This powder can be kept at room temperature. It can be sent somewhere, for example, or it can be used immediately. So what we've tried to do is we've tried to leave it on the bench, and the longest we've left it so far has been 3 years. We've also posted it to our collaborators because we wanted to see if it will survive the normal post without cold chain. And we've also done a lot of experimentation, obviously. We've heated it, we've really tried lots of things to see if silica is as protective as we want it to be. So once we've done all of this, obviously, we want to release the protein out because we want to check that it's working okay and still has its structure and the nature. So we have devised a release protocol. So on the right-hand side here, you can see that we have a release protocol where we add the release buffer to our powder. We end up with a mixture of the protein and the silica, which then can quite easily be separated. And now this protein can be used, or we obviously have spent a lot of time studying those proteins to show that they are still intact. Just to show you visually, you can see the difference here. On the left-hand side, we have a solution of the protein, so nothing happened to it yet. This is just protein in the buffer. And then after 2 minutes, after we've added silica, you can see already that the whole solution became cloudy. So here we already have formed our nanoparticles. And because of that, we can see the cloudiness. And eventually they crush out, or we can remove them and quench the solution if we want to. So obviously, depending on how big we want our nanoparticle to be, we can control that. We can control the time. And we also can control the temperatures. So if we do it at room temperature, it happens slightly faster. If we do it at lower temperatures, it's slightly slower. Because it's a diffusion-driven process, temperatures affect the formation of it. But we can control the size of the nanoparticles which are being formed, obviously. I'm going to show you some of the results here. If you haven't heard of some of those techniques, don't worry. I'll explain it so that you'll understand the main message from those results. So I'm going to go through some of the proteins to show you some of the results. So this is one of our earliest results where we've looked at hemoglobin. So here on the left-hand side, we're looking at the infrared data. And in the green, you can see that it's a data for silica itself. And we can see here quite characteristic peaks, around 1,200 inverse centimeters. In red, I'm showing you native hemoglobin. You can see that it has quite characteristic amide peaks, about 1,651 and so forth and so on. But when we mix them together, when we look at the insilicated hemoglobin, you can see both signatures. You can see the signature from the silica, and you can see the amide peaks from the hemoglobin. So these were our first results where we wanted really to see that we are successfully incorporating the protein into silica. Obviously, we needed to show that the protein is inside and not just on the surface. So we did a lot of experimentation where we've heated our proteins and then looked at how they have survived. So on the right-hand side, I'm showing you circular dichromosome data. circular dichroism, it's a technique which is sensitive to the chirality inside the proteins. So if the proteins have chiral loops in them, like alpha helices, for example, you get a signal. So you can see here that hemoglobin shows a nice signal in green here for the native, but then the insilicated one, so this is insilicated and released protein, shows exactly the same signal. So there's slight changes here, but nothing really big. And then what we did also is we insilicated it and heated it in order to denature it, and then released it and looked at it. And again, you can see that the circular dichroism data is very similar. Crucially, we see in red here a native heated hemoglobin, which was heated to the same temperatures. And you can see that it's completely denatured and lost any chirality inside that protein. So we can see a big difference between the unprotected and protected proteins here. So here we're looking at some of our latest data, which we just published last year. This was done on an SBI antigen. This is an antigen which we hope that in the future will be used instead of the old BCG vaccine. So it could be a new vaccine against tuberculosis. We did exactly the same thing here. We've collected the circular dichroism data, but we've heated it gradually. And as we're heating it, we looked at how it denatures. And on the right-hand side, we're looking at the 2 data points for the native and for the insilicated and released sample. And again, we can see that we are not seeing any differences in the after the insilication and the release. Looking at the enzymatic activity, again, we're seeing interesting things here. So here we've looked at lysozyme enzyme. So lysozyme, it's called lysozyme because it's lysis. It breaks down the bacterial walls. It's our first defense against infection. We have lysozyme enzyme in our tears, in our saliva, and in many other glands in the body. So it breaks down bacterial walls. So here we are looking at how good it is at breaking bacterial walls. And you can see here on the left-hand side, the activity from the pure lysozyme, so nothing was done to it. The second column is for the insilicated release lysozyme, so again, we're seeing similar activity. The third one shows for the insilicated heated one. So this is the one where we've protected it and then heated it to see if it would denature. And you can see that we've lost some of the activity, but majority of it is still there. And crucially, if you look at the last column, you can see that the unprotected lysozyme, which was again heated to the same temperatures, has completely denatured and lost any activity. So crucially, we can see already through all of those experimentation that we are seeing quite a good level of protection, which insilication is affording in different proteins. So I've already showed you 3 different proteins so far. So this is the latest data, which we've just published very recently. So this is the data for tetanus toxoid fragment. So it's TTCF, tetanus toxoid C fragment. This is a really interesting data. So here what we did is we insilicated TTCF, and we took several batches of it. We took one batch which we've insilicated and heated, and we took another batch we've just insilicated, and another batch which was not insilicated, nothing was done to it. We then sent all of those batches to our collaborators in Newcastle. So it took several days for these samples to arrive, and they were sent by normal post. No refrigeration, no cold boxes, nothing. So this is completely completely normally sent samples. So on day 0, these were injected in mice, and we have here 4 groups of mice. And then every 7 days, we collected plasma and blood from the mice in order to see what kind of immune response has been developed due to this injection. You can see here that after 20 days, we see quite a good response. and it's on par with native TTCF. So native is in blue here, insilicated is in green, and insilicated heated is in yellow. Crucially, what we are seeing is that the heated native one has no immune response at all. Then on day 26, we give a booster here. And then after that, again, we continue looking at the immune response, which is rising again in the 3 samples, as you can see. And crucially, the insilicated and even the insilicated heated ones are showing really good comparable response to the native ones. So this was a really ultimate proof for us to show that we are preserving not only the structure, but also the functionality of our proteins, which then can be used as vaccines in the future. So this was our first in vivo study. Since then, we've actually done a second in vivo study, which we are writing up as a publication at the moment. So it's a really exciting time at the moment. So just to explain to you how this whole process happens. So on the left-hand side here, you can see the protein. So this is TTCF. When we add silica to it, you can see that there are regions where we see those green dots. So the green dots indicate silica. So green dots come in contact with the protein, and they really like the positively charged areas of the protein. So when the protein has lysines or arginines in their amino acid chain, these are the areas where silica gets really immediately attracted. And from then on, those green dots, they start growing into a chain. So this is where the polymerization of the silica starts happening. You can see in the second panel here that we get this green area, which is the first layer of silica, which surrounds the whole protein. And then we have the formation of the second layer, which is in blue here. And again, it goes all the way around the protein. And very rapidly, we get many layers of the silica all surrounding the protein. Because silica is an inorganic material, it's slightly harder compared to the protein, obviously. So it's almost, you can think of it almost as a shell. So it's like a turtle shell. So you have a turtle inside, and then you have a shell which is protecting that turtle on the inside. So as the silica layers grow, they then sort of bring together those individual particles. So those individual nanoparticles, they sort of start sticking together. And eventually on the right-hand side, you can see the SEM image of the final material. So this is TTCF inside the silica. You can see sort of almost rounded particles here. The reason why they look rounded is because those particles, they actually consist of hundreds of nanoparticles, of individual nanoparticles with individual proteins inside them. So that's why at the end of the process, what we are mainly seeing is actually sort of rounded nanoparticles, which is consistent with the silica which we normally grow. So you can see here that we've developed a novel method. We call this method insilication, which we hope will be breaking the cold chain for the vaccines in the future. So so far we've developed an insilication method for tetanus vaccine. We're working at the moment on diphtheria. We've almost finished diphtheria, and we want to also work on pertussis, because that will help us to develop the insilication for the whole DTP vaccines. So as you know, there are some vaccines which are given all together. So for example, MMR or DTP. There are also some even bigger ones like pentavalent vaccines, for example, where we have 5 vaccines. So we want ideally to replicate this. And in an ideal case, we want obviously to have an insilication of all of them together so that they can be given to patients in the same manner. We're also working on optimizing the release, because at the moment, the release is not very easy. It's easy for us as chemists, obviously, to do in the laboratory, but it's not very easy for medical staff. So we want to come up with the method which then will make it easy for medical staff in the field to release and administer. Also, we are applying this method to other targets. So we've already started looking at therapeutic antibodies. We've looked at 2 antibodies against breast cancer. And what we find with antibodies is actually the method works really well because antibodies are quite small, but also antibodies have to be frozen. So they have to be stored not just at 2 to 8 degrees, they have to be stored at minus 80 degrees, which is even bigger problem. And since we're seeing that the insilication is really helping with antibodies, we think that there is a big interesting area there, obviously, for us to be able to see if we can insilicate those more in the future. Ideally, I'm interested also at looking at some drugs. It would be interesting to see if we can insilicate antivenom drugs. This is something we haven't tried yet, and it would be good to insilicate them because obviously antivenom drugs are not used often enough to be able to store them. So if we can make their storage sort of long-term more, it would be really useful. In terms of the administration to patients, our chemical release works really well today, but it's, as I said, a little bit hard at the moment. So we are at the moment trying to make it as easy as possible. So we're actually working on a new syringe, which we hope would contain the insilicated vaccine. And then also the medics, obviously, they are used to using syringes. They will compress, and then it would release inside the syringe, and then they can inject into people. So this is something we are still developing at the moment. Also, it's quite interesting that silica can be delivered orally because silica is actually FDA approved as a drug delivery system. So a lot of the drugs today, which we are taking in tablet form, they actually consist of silica already. So it would be interesting to see if we can look at some of the drugs which are unstable at room temperatures and insilicate them, and then try and see if we can make them stable so that people will not need to refrigerate them. The one drug which therapeutic, which we've already thought about and started looking at is insulin, because obviously insulin has to be stored in refrigerators and it goes off after about a month, which is not ideal. And there are lots of other drugs which where insilication could afford us good storage of those drugs. So this is something I'm interested in looking at. And if somebody is interested in doing something in that area and wants to collaborate, I'd be very happy to. So I wanted to acknowledge all of my collaborators, my postdocs, my students, all the funding bodies who have funded our research. And I wanted to say a big thank you to you for your attention. I'm open for collaborations. If you have really interesting systems which are not stable today and you want to make them stable, I'd like to hear from you. Please email me or find me on Twitter. Thank you very much.
So, Asa, thank you very much for that excellent talk. So we're gonna try and fit in as many questions as we can. I'm gonna start by asking, why is it that some vaccines can be kept at room temperature while others can't? So you mentioned polio vaccine and a few others that actually do not require refrigeration. So what makes them different?
So, okay, so we have different formulations. So with polio, there are about 10 different formulations. So some of those formulations, so they're all very different, first of all, structurally, but also some of them can be lyophilized. So lyophilization is a freeze-drying technique, which is used today to make vaccines stable. So if vaccines can be lyophilized, then that really extends their shelf life, and it also affords for them to be able to go at higher temperatures and be okay. For some vaccines, first of all, we cannot lyophilize them. So for example, anything with adjuvant is not going to work. Also, the influenza vaccine, for example, is a good example. where it's incredibly unstable. So even, if you open the fridge several times and you have influenza vaccines in front, you have to discard it just from opening the fridge a couple of times. So it's really, really unstable. So it comes to the formulation itself. So the protein which makes the virus or the viral particle, or the protein which makes the vaccine, if it's really less folded, let's say, it makes it much more unstable, and it's very hard to predict whether vaccine which we will make in the future, whether it's going to be stable or not. The only way to do it is the way it's done is they make the new vaccines and then they look at its temperature stability. And then obviously if it's really unstable, it has to be refrigerated. But if it's not so much, then we can maybe take it out for a little bit, and that's not a problem.
Okay, thank you. At the beginning of your talk, you mentioned that insilication was a process that can be used for protein-based or viral vector-based vaccines. So what other types of vaccines are there? You mentioned RNA-based or DNA-based, and why would those not be suitable for this?
To be honest with you, it maybe is possible to do this method on RNA and DNA-based vaccines. We just haven't tried yet. So that's probably would be the short answer. The slightly longer answer is the DNA structure is much more negatively charged compared to a lot of the proteins. So that's why we sort of haven't really tried to look at it, because you see silica is attracted to the positive charges in the proteins. And that's why a lot of the vaccines which we use today, which are protein-based, they're much easier to insilicate. We haven't really tried RNA or DNA. This is something which we will probably do in the future. And if it works, maybe we can also do the RNA and DNA-based vaccines too. We've already tried peptides, actually, and that works pretty well too.
Okay, so is there a difference actually with the charge of the proteins? Because some proteins are very negatively or very positively charged.
Yeah, there is actually a difference. Yeah, so each vaccine, even the same vaccine but different formulation, can have very different charges. So, for example, the polio vaccine, also when we looked at some of them, between different formulations, they can be differently charged. So yeah, the charges are very different. So it would have to be on individual basis at this stage, because we haven't really come up with the sort of global method which would work for everything. So one of the things which I'm trying to do at the moment is I'm trying to, we've already tried 13 different targets, but I'm trying to do as many targets because I want to see if there is like a rule which would work for all of the structures, or at least for some classes of the structures. Because if we have some kind of rule, then we will be able to then sort of predict, and also we'll be able to come up with some kind of system for understanding on looking at different classes. You see what I mean?
Yeah. So how are you choosing which vaccines to try first?
That's a good question. So the whole idea came to me when I took my daughter to be vaccinated. So I gave birth to my daughter in 2010, and 2 days after she was born, I took her to be vaccinated with BCG vaccine. So this is vaccine against tuberculosis. And this is when the doctor took out the vaccine from the fridge, injected in my daughter, and I started questioning him and asking him, why does it have to be cold? And he sort of looked at me and said, are you crazy? It has to be cold because it's going to spoil. So because it's all started by thinking about children vaccines, in my mind, I really want to look at children vaccines. And that's why we chose DTP. Partly because tetanus is quite easy to get hold of, but also because it's part of this DTP vaccine. And DTP is a model vaccine for WHO. So WHO really looks at how it's being transported around and how many people are being vaccinated with it. So if we can solve the DTP vaccine, and if that's being used all around the world, I think that would be a really great model to use in the future. So my next target after that, what I want to do is I want to do Hpv vaccine. So this is the vaccine against cervical cancer, which is given to girls when they are about 13 years old. And then obviously the obvious cases would be MMR, BCG, and all the other childhood vaccines. There are about 15 of them.
Okay, so Rodrigo Contreras is asking us if there are any molecules that cannot be in silicated due to their chemistry.
Yeah, this is a true scientist question. Yeah, so yeah, so yes, we as I already said, we've already done 13. We've actually tried 14. One of them has not worked. And it has not worked because it's an incredibly negatively charged protein. So we couldn't do it before, and this was pretty much in the beginning when we were starting it. Actually, lately we've developed a new sort of protocol on how to do it. So we are now thinking that we can probably revisit it again and see if we can use the new method. Because with the new method, we can add some other additions to trick the silica to think that the protein is more positively charged. And so with this method, we might be able to do it again. But yes, out of the 14 subjects we've tried so far, one did not work. So yeah, there are some examples where it probably may not work.
And is there a limit to size of the molecule?
No, there's no limit to size. So we've actually tried quite a variety of different sizes so far, between really small peptides and quite large protein complexes. We've actually tried a bacteriophage, a really large bacteriophage, and that worked too. So it seems to be, the size doesn't seem to be imparting any problem. What's really more problematic is really the charge. This is really where we have to play. So the charge of the protein is more important. So we now, every time when we start with a new protein, the first thing we do is we really study the charge and we really study the amino acid sequence to see that it would have at least some of the positive amino acid chains for us to hook our silica onto.
Okay. So are there any other materials in addition to silica that can be used for this type of coating?
Yeah. So there are lots of groups around the world who are working on this problem, which is really great to see. Actually, I'm really happy that there are a lot of us are looking at it. So there are groups who are looking at polymers. So they're applying sort of a very similar, in a very similar way, they're applying polymers on the proteins. There are also groups who are applying sugars, so carbohydrate molecules, and again, those carbohydrate molecules stop the proteins from unfolding again. There is another group which is working on trahylose, so they're using trahylose to stop the proteins from unfolding from these entropic problems. So yeah, there are lots of interesting ideas all around the world, and yeah, it's really good that we are all working towards the common goal, because as I said before, our method may not work for everything. It may not be the silver bullet. It may work for some protein, for some vaccines well, but it may not work for all of them. So it's good to see that there are lots of other things which are happening, so that we can come up with as many solutions as possible for this problem.
Okay, so Jose Llamas is saying, well, first of all, he's saying it's an amazing talk and an amazing work that you're doing. And he's also asking whether silica can work as an adjuvant or coadjuvant of in drug delivery.
Yeah. I don't know if you've noticed this or not, but in all of our data, and we've noticed that consistently across all of our data, is that when we get the immune response or when we get with the enzyme response, after the protein has been insilicated, we always get a rise in the response. So it's almost like it's acting like an adjuvant. So, I mean, so far we don't have a definitive proof for that. Silica is already being used as an adjuvant in some cases, but not in all of them. But so we may not, we may need to do more studies in order to really show that it acts as an adjuvant. But yes, I do think that it probably will work as an adjuvant. But obviously, we will need to have more data to be absolutely sure about that.
Okay, so one other question is, do you have any plans to start doing trials with human subjects?
So in order to start the clinical trials, we will need to have a partner. So we're actually talking to several vaccine manufacturers at the moment. And obviously with the pandemic happening at the moment, everything has been sort of scaled down a bit. But we are hoping that we may soon be able to start doing small scale studies. So this would be phase 1 kind of studies, where we can look maybe at small number of people. But to be honest with you, just to make sure that everything is working okay, I really want to run maybe 2 or 3 more animal studies before we go into humans, because obviously we need to be absolutely sure that there are no problems at all. And once we have that, then we will proceed into humans. Yeah, I don't want to rush it at the moment, but yeah, in the future, there are definitely plans to do that.
Okay, so talking about the pandemic, what are the implications of your research in terms of the current developments of a vaccine against COVID-19?
Yeah, so I was expecting that question. So obviously COVID-19 is a viral infection. And obviously, a lot of the research which is happening at the moment is looking at developing vaccines either on a virus-based or on a spike protein. So almost all of the research is being done on some kind of protein. So I'm really waiting at the moment to see which of the vaccines will work, because as soon as we have a vaccine or vaccines working, then we can really start looking at trying to see if we can ensilicate them. So I'm actually in talks at the moment with the Vaccine Manufacturing and Innovation Center in UK. It's a new sort of entity, which is part funded by manufacturers and part funded by the government. And the idea of this sort of center is that they want to stockpile vaccines, and they also want to look at the safety of the vaccines. So we've been already been in talk with them about both of this. So firstly, we want, if they want to stockpile vaccines, they obviously want to use the best methods for preservation of the vaccines, because you don't want to stockpile something in 1 year and then throw it away next year. This would be crazy, crazy waste of money. So we've been talking about applying our method to see if we can extend the shelf life, because we've already seen that insilication can extend the shelf life of the proteins. In terms of the good manufacturing, again, this is another area which we are talking to them, because we want to work with the best companies who are producing vaccines today, because we want to just incorporate our method as just one step in the manufacturing process. To make it as easy as possible for manufacturers to implement it. So yeah, it's something which we are trying to do at the moment. We are in talks, but obviously there isn't a vaccine yet at the moment. But as soon as there is something, we will be able to jump on it and see if we can ensilicate it, which I have really high hopes that we will be able to do.
Okay, so I guess a somewhat related question to that is how expensive it is and how scalable it is, because looking at your talk, it looks so simple, or you almost had like a flask and then you spin it and then out in a few minutes you get the insilicated molecule. So is it really that easy?
It's quite an easy process, yeah. So everything what we've been doing for quite a while has been based, we call it a beaker process, yeah. So we just use a beaker and we add everything together and it works. In terms of actually scaling it up, we've been seeing over the last 2 years, we've been actually working with chemical engineers because we want to change our process slightly. So instead of using the beaker, we've actually been looking at doing sort of a continuous process where you have a tube. It could be a long tube, for example, and then you flow your protein in, and then you add silica to it, and it's flowing through. And as it's flowing to you, you can control the size much better. And because you can control the size much better, the whole process is much faster. And you can flow quite a lot of product through, which means that the production is much easier. So scaling it up becomes much easier in a flow process. So this is how a lot of the pharmaceuticals produce their products today, because it's a much more scalable process. So yeah, this is something which we've started looking about 2 years ago, and it's still sort of under development, but it's working pretty well now. So we are really hopeful that it should work for the manufacturers in the future. Yeah. And also it's a really, honestly, it's a really simple process, because silica is such a simple material. It's sand. It's sand, and it's really abundant, and it's quite cheap. So it makes it, so obviously, because we will be introducing an extra step in new manufacturing, it's going to make it a little bit more expensive, but the overall impact of not refrigerating the vaccines is going to cancel all of that expense in the future.
Okay. So we have a question. Okay, so Angie Hernandez is asking whether there's any studies on the toxicity of nanoparticles, and and she's also asking about clearance from the body in animal tests, and whether this increases the amount of active vaccine that comes out of the body because it's coated, so probably more of it will be preserved and potentially contaminate the environment still as an active vaccine.
Yep, I understand. Yep. So in terms of the silica toxicity, silica is really non-toxic. I mean, it's already FDA approved. So actually, what we find quite interesting is that some of the targets which we've been looking at, they're not FDA approved, but the silica is actually. So the coating is FDA approved for oral delivery already. So the reason why it's okay for oral delivery is because the body can digest it, and also what we're using in for the oral delivery are not nanoparticles, but they are microparticles. Yeah, so that's fine. So silica, actually, there's been quite a lot of studies on the silica toxicity, and silica is toxic, but only if it's inhaled. So if it's inhaled, it can be toxic for the lungs. So that's the only process which is not good for the body. But if it's being injected, actually silica is fine to be injected intramuscularly. It's also, it surprised me, but it's actually okay to be injected even intravenously, which really surprised me. But obviously, in our case, we don't want to inject anybody with silica. So in our method, we've actually devised complete release. So when we release our protein, we separate completely the silica and the protein. And we've done actually considerable studies to show that there's absolutely no silica left in the protein solution. So, I mean, we've done really extensive study. I can give another talk about it, which I decided not to include here. But yeah, we've done a lot of studies, because obviously at the end of the day, this is going to be injected into people, and we don't want to inject people with silica, even though silica is okay to be injected, apparently, which really surprised me too. So yeah, that's the answer.
So just to be clear, what this means is that you're removing the silica coating before the injection, or?
Yeah. So for our mice studies, we've released our protein out. We've separated the silica and the protein. So we are only injecting the protein, and we've been injecting only the correct amount. So for example, as you know, when you take the vaccine, the majority of the constituent of the vaccine is actually not the active ingredient. It's actually some adjuvants and some, sometimes they use some preservatives. So most of what there is in the vaccine is actually not the vaccine itself. The active ingredients, so for example, the toxin or the protein or the virus, it's going to be a really, really small constituent of that vaccine. So obviously, when we were doing our studies, we had to scale down after it's been released. So we actually do, we do our experiments on micrograms. So we usually produce about, let's say about 50 micrograms of the silica in the powder form. But inside that 50 micrograms, there is quite a large amount of protein. So when it's being released, it's actually multiple, it could be multiple doses of the vaccine in the future.
Okay, so Elvira Garibay is asking us, if vaccines are useful, why is it that so many people get sick still? And she's also asking whether isn't it better just to let nature run its course, and whoever gets sick, tough. So why do we want to use vaccines in the first place?
Okay, why do we want to use vaccines in the first place? So we are vaccinating against potentially lethal diseases. So let's say, for example, if we take measles, yeah? In most of the people who will get measles, it could be just like a flu or really bad flu, for example, yeah? The problem is that in quite a large number, well, it's still going to be a small number, but still in quite a large number compared to, let's say, 1% or something like that, it could be a really, really bad infection. It could actually lead to lethal consequences. But between lethal and mild infection, there is a big variety of different ways the person could be ill with measles. So, for example, it could lead to really bad consequences like encephalitis, or it could lead to pneumonia, it could lead to other things. And potentially the person may not die from the measles, but the person could die from something else, which could be a secondary thing from measles. So that's one thing. The second thing with measles is that the measles actually strips the immunity. So the latest data on measles has shown that it strips the immunity of the body. So for example, if the person had a cold before, but then if they have measles removes these antibodies. It kills those antibodies, which means that this person again could have quite bad colds or other diseases. So it's quite there could be quite bad consequences. If you take mumps, for example, mumps again, it could be a mild disease, but in up to about 50% of boys, it could lead, as a secondary effect, it could lead to sterility in the future. So it's quite a bad consequence for a lot of children. So as you can see, the children may be recovering okay when they have it, but then in the future they may have really irreversible consequences happening. So that's why we want to vaccinate people against those diseases when they are small, obviously. So this is just two examples. If you look at some other examples, polio, again, it could have been a mild infection, but in some bad cases, it actually could paralyze people. And you never know who will be paralyzed or who will have a mild infection. And because you don't know the consequences, it's much better to immunize the person so that the person does not have this really bad disease rather than just take it to the chance. So, I mean, I can give you lots of examples where the consequences could be dire for people. In majority of the cases, yeah, the best case scenario is immunization. Sorry, what was the second question there? There were two questions.
So the second question is, if vaccines are so good,
why we
still get, and she's asking specifically about influenza. So every year, lots of people get the vaccine, and many of them still fall ill with the disease.
Yeah, so influenza is a problematic one. So influenza has quite a lot of mutations, which means that there are different strains which we can immunize against, but there are some strains which we cannot immunize against. So when you get the flu vaccine, so I've just booked my flu vaccine for this year, which I will take next month. And when I will be vaccinated, I know that I will be protected against some of those strains. So hopefully I will meet in the future those strains, I'm hoping, and I will not meet the strains which I'm not immunized against. So this is the problem with flu vaccine, is that it's not a silver bullet, it only would immunize you against some of them. So what happens is that every year, scientists just look at what's prevailing in that year or what was it in the previous year, and they make a guess at what strain will be active during the year. And by guessing so, they're actually putting those strains in the vaccine. So unfortunately, we are not immunized against all of the strains, and that's why we still can get ill. Yet I'm still going to say that it's much better to be immunized, because if you immunize yourself against flu, you are at least immunizing yourself against some of those strains. That so it will give you some protection, which is a good thing. Having said that, now if I just expanded to all the other vaccines too. So if you look at any vaccine, it always says that each vaccine has some percentage of efficacy. So for example, if you're immunized with MMR vaccine, MMR has efficacy of, I don't remember exactly, but I think it's like 90%, which means that there is still 10% chance that you may get infected with those diseases, even though you have been immunized. It's not 100% protection. So we will get 100% protection only if all of the people around us are immunized. So if we are sort of inside a bubble where the infection cannot get through, only then we are all going to be 100% protected. And that's why it's quite important to have really high rates of vaccination. So if you remember in my talk, I've mentioned that we want to have herd immunity. So we want majority of the population to be vaccinated. So we want to have 90% at least to be vaccinated, because if we have 90% population vaccinated, then we can have that bubble and everybody protect each other. And then we really see the drop in the infections happening in that case. So I'm very pro-vaccination.
Okay, yeah, I think we should all be. So Etelvina Carrada is asking about which commercial vaccines have been used in instillification. I think you've covered that. In the interest of time, we also thank Jacob for his or her question, but I want to. So I'm sorry we won't be able to get to your question, but thank you very much still. I would like to ask you one last thing, and this is about how did you become a scientist? Because I know your story, Isel, and it's really inspirational. So if anyone is listening to us today and is thinking about, well, maybe I'll pursue a career in science, what do you have to say about your own story and anyone who's thinking about it?
So in my case, I came from, so I was born in Kyrgyzstan in Central Asia. I was born during the Soviet Union. So when Kyrgyzstan used to be part of the Soviet Union. So Soviet Union break down when I was about 11, I think. So I was in school at the time. So when I was growing up, I went to Russian kindergarten, I went to Russian school, and then I went to Russian university. So when I went to the university and I said I wanted to become a scientist, my family were horrified about it because I come from a family who have mainly humanities background. So my mom has been doing a degree in ethnography and history. My dad was doing a degree in design and sort of arts. And most of my relatives are from humanities background and have worked with languages mainly and education. So yeah, when I was entering the university and I said to my parents, I want to enter, I was thinking of physics in the beginning. My mom was just a bit horrified, and she was trying to steer me into something softer, as they were saying. So she was trying to steer me into journalism or philosophy or something like that. But I think partly it's due to the fact that the Soviet Union broke down when I was 11. So you see, the whole country sort of collapsed around us. The whole system has collapsed. So it was sort of a new era in our country. And it was really destabilizing for all of us, obviously. And I think in a way, I really wanted some stability in my life. And also due to some personal circumstances, I really wanted stability. And for me, sciences sort of represented that stability, you know, something which is not subjective, something where you can't just say, oh, I don't like 2 + 2 = 4, you know. I want 2 + 2 being 5. No, it doesn't work in science, yeah? So science has facts. And I think this is really what I wanted. I wanted some stability. I wanted something more solid foundation. Also, I'm thinking back now. I'm thinking probably it was my rebelliousness, because we all rebel against our parents at some point, as a lot of us know. And in a way, I guess I was trying to rebel in that manner against my parents. Yeah, it's also all came together. At the time when I was entering the university, so I went to study sciences, and to be honest, it felt like a lot of my relatives did not believe into me. So in Kyrgyzstan, especially because it's such a small country and it's such it's a very sort of it's more like agricultural country, you know. So majority of the girls are not really being pushed to do something with their life. So we are really being told to just stay home, have children, get married. So this is sort of the aspiration we have. And I really didn't want that. I wanted something new. And again, due to the Soviet Union collapsing, suddenly these borders were open, and suddenly I could see that I could go somewhere, I could do something with my life. And I think all of that sort of came together and pushed me into going into science. It's true, I was the only Kyrgyz girl on my course when I was studying. And really a lot of teachers did not take me seriously in the beginning at all. Only later on, when I sort of became really serious, and I won an Olympiad, 2 Olympiads in Kyrgyzstan at the time. So only after that I sort of got respect, and it became sort of a little bit easier to study. But when I got my scholarship to go to Cambridge, that was really a big thing for me, obviously, and that really pushed me to really look much wider and sort of open my horizons, and that really helped me to, I guess, sort of grow as a person and as a scientist.
Thank you very much, Aysel. Thanks a lot for the presentation, and thank you to everybody who has been listening to us, and everybody at Colegio Nacional who are amazing, and they're open their doors and all their platforms for these talks. Thank you as well a lot to Fundación UNAM for all their support in all these conference series. So I think I just want to finish by inviting everybody to our next talk. So I'm gonna switch to Spanish now. Muchísimas gracias a todos por acompañarnos este día. Y bueno, le agradecemos a Isel Sarteva por su excelente presentación. Creo que es un tema muy relevante. La siguiente semana, a la misma hora, también el martes a las 12 del día, vamos a tener otra presentación de la doctora Marian Marchand de la Universidad de las Américas en Puebla. Su tema va a ser migración, retos y realidades. Creo que es un tema también muy, muy relevante para nuestro país. Y quiero cederle entonces la palabra al doctor Jaime Urrutia y al licenciado Dionisio Meade para que nos den unas últimas palabras y cerrar esta sesión. Gracias.
Thanks very much, Isel. It's a very interesting presentation, and congratulations. It's an impressive research, and I like the way you present this. Look how easy it is, and yeah, I suppose it's easy once someone like you do it. So thanks very much. And it's not only an impressive research achievement, it's also extremely useful. As you mentioned, keeping the vaccines active is a big challenge. And yeah, and great that you took this project and you have you succeeded.
Thank you very much. Thank you.
Switching to Spanish, and bueno, muchas gracias a todos por acompañarnos. El estudio que nos presenta Isel Sarteva es realmente extremadamente útil, y es bonito escuchar cómo alguien con esa pasión puede presentar algo como, miren, que es sencillo resolverlo, cuando en realidad presenta un enorme nivel de dificultad, y es todo un reto. Es una manera interesante de ver cómo cuando alguien tiene una idea y la sigue a fondo, eventualmente se logra el éxito. Entonces, realmente yo creo que vamos a escuchar mucho de Isel en los siguientes años por venir. Le deseamos realmente mucho más éxito por el bien de todos, en realidad. Y nuevamente, pues muchas gracias a nombre del Consorcio de Universidades por la Ciencia. Los invitamos a que nos sigan acompañando en estas presentaciones, y les invitamos también a que nos acompañen en el Foro 2020 de Fundación UNAM, que está dedicado a las lecciones de la pandemia. Entonces, realmente un placer. Thanks again, Isel, and great, we are in contact, and we look forward to have you here in Mexico. You are always welcome. And
Thank you.
pasamos la palabra a nuestro presidente de Fundación UNAM y el licenciado Dionisio Meade. Y pues nuevamente, gracias a todos los que nos escuchan.
Pues muchas gracias nuevamente por acompañarnos, muchas gracias por participarnos en la realización de este evento. Gracias, Isel. La presentación que tú haces incide realmente en el bienestar de las personas, y hay que ver siempre con entusiasmo, con simpatía y con gratitud cómo hay gente que dedica su vida a la investigación y a la ciencia. Nos parece muy relevante que podamos compartir estos conocimientos, y yo creo que esta es una de las enormes ventajas del consorcio. Hoy tenemos la presentación de una formidable investigadora de la Universidad de Meade, pero las hemos tenido de otras universidades que participan en el consorcio, y las hemos tenido también de los propios expertos de nuestra Universidad Nacional. Esta es la suma, este es el enfoque constructivo que deriva de un evento como este que hemos celebrado hoy, pero es también las posibilidades que ofrece un vínculo, una alianza como la que se deriva también de la participación de tantas universidades que forman parte de este consorcio. Además, la motivación implica también ir sensibilizando a muchos de quienes se están formando para que vean en la ciencia un proyecto de vida. Esto que nos platica Excel, la forma en cómo se convirtió en una vocación científica, debe de motivar a muchos otros de nuestros jóvenes que se están formando ahora en muchos países a la luz de las capacidades que ofrece el consorcio para ir realizando este potencial, para ir desarrollando esta vocación de invitación a la ciencia. Los temas que hoy nos presenta son bien valiosos. Habrá vidas que se puedan salvar de continuar avanzando con éxito en estos programas y por eso debemos ver con simpatía y apoyar siempre con todo nuestro entusiasmo la investigación científica y el desarrollo tecnológico. Gracias, Excel, por tu presentación. Gracias, Jaime, por convocarnos a participar de este esfuerzo. Gracias, Araxi, por esta idea formidable del consorcio. Gracias a la Universidad de las Américas, al Colegio Nacional y gracias, desde luego, a nuestra Universidad Nacional por sumarse en la realización de este esfuerzo. Como dice Jaime, el próximo jueves en la tarde vamos a tener nuestro foro 2020, las lecciones de la pandemia, y va a ser especialmente relevante porque habremos de conocer qué está haciendo la universidad para luchar contra el COVID. Y ahí habremos de escuchar también, en otra perspectiva, la investigación científica que está realizando en sus distintos espacios la Universidad Nacional, y habremos de ver también, y habremos de verlo con satisfacción, cómo nuestra UNAM liderea y participa activamente en la investigación científica en la lucha contra esta pandemia. Muchas gracias a todos y los esperamos también el jueves en la tarde. Gracias.